data set that comes from Pi data sets called polio trials and is the results of the 1954 field trial tests of the Salk polio vaccine and the data collected also in 1955 from the NSF, or excuse me, NFIP. Okay. Um, and we're going to this data set, as I talked about previously, it has two data collections that were done. One of them was a randomized control, and the other one was an observed control. The data that we're going to be talking about today lives right here, and we're going to focus on the randomized control experiment in which people were assigned to the vaccinated group or to the placebo group. Okay, and you can see the data down here. Roughly half of the population was assigned to the vaccinated, half to the placebo, and we see that the observed counts of paralytic polio in the vaccinated group are much less. They're 33 compared to 115. We'd like to know, what are the chances of just getting 33 paralytic polio cases um, and having this data occur just by random chance? So let's first review some things last time. So we reviewed conditional probability. If you're in the vaccinated group, your chances of paralytic polio are given here, and it's about 0.01 of a percent. Um, if you were given the placebo, no vaccine, then your chance of paralytic polio rose to be 0.05 of a percent. So neither outcome is super likely, but one's a lot bigger than the other. Is this just due to random chance? Are they independent? Technically, independence, if we have population probabilities, would mean they're independent if either of these two conditions are met. We'd previously tried calculating this, and we saw that the conditional probability, if you were given the vaccine, was not equal to the overall rate of polio in the data set. So uh, if you are assigned to the vaccinated group, that's your rate of polio, as opposed to the general population, that is the combined population, it's that, which is about, which is considerably higher. But the problem is with this independence, we have to have the population probabilities, and we don't have that. The data we have is from a sample. So how can we take into account the randomness of the sample and assess it? Okay, we're going to use the hypergeometric distribution to assess this claim of independence, viewing the groups as random assignment, because that's what was done. People were randomly assigned to treatment and control. In doing this, we'll be testing our first hypothesis, and we should state our null and our alternative. The most common statement at the null is that the two variables are independent. That is polio and vaccination. Okay? Those two variables have nothing to do with one another. Phrased another way, assignment to treatment or placebo has no effect on the outcome of paralytic polio. Okay? The alternative is that they're dependent. They're not independent, which means the assignment to treatment reduces the chances of paralytic polio. Okay? We could have also said the null is, excuse me, Um, so when we calculate this probability to assess the null and alternative, what we're going to do is we're going to assume that the null is true. And if the probability is so unlikely that we don't think we could have actually observed our data, that's called the significance level, then we're going to conclude that the null hypothesis is false. the null hypothesis is not consistent with the data. Okay. the the hypergeometric distribution is given here, and what we're going to do is we're going to calculate a p-value. P-value assesses how likely the observed data is, um, and we have an observed data of 33. Um, so because 33 alone, there is other evidence against the null hypothesis. So for example, if it had been 32, 30, 31, we're going to calculate the probability of 33 or less. Okay. Now, this hypergeometric distribution, it naturally calculates probabilities of 2 by 2 tables. So in this example, our sample size is about 400,000 roughly. And in this population of about 400,000, the exact value is listed there in the text. So that's the exact sample size. In this population, there are 148 individuals with paralytic polio. Now we're randomly assigning individuals, half to the vaccinated and half to the placebo, roughly. Okay. Here, uh, this value minus this value gives us that value, the non-paralytic group. And if I know one of these values, any one of these values on the interior, so for example, if I know 33, and I know these column totals, these two, I can reconstruct the entire 2 by 2 table. Okay, so this hypergeometric distribution, it is a natural way to calculate probabilities that correspond to 2 by 2 tables. And what we're going to calculate is we're randomly assigning half the population this, and the population here has a total of 148 cases of paralytic polio. Half of it's going to the vaccinated group, half is going to the placebo group. What's the probability that we're assigning 33 or less cases of paralytic polio? Well, we can calculate that with the hypergeometric distribution and calculate the probability of 33 or less with these specific values. Okay, so this is the size here that gets assigned uh, to the vaccinated group. That's our sample size. These are the ones with the trait of interest, and this is the total population size. So we calculate that, and the probability of 33 or less cases, i.e. that we happen to randomly assign 33 out of the 148 to the vaccinated group, is 4 times 10 to the minus 12. That's a tiny percent. It's way less than 1%. So it would make observing the given data extremely unlikely if we just happen to randomly assign them to that group. It must be that, uh, you know, we shouldn't have 33 if the null hypothesis was true. It'd be something more like half, right? We'd expect to get half of the paralytic polio cases. Um, but, uh, because this isn't consistent with the null hypothesis, in the language of statistics, we'd reject the null in favor of the alternative and conclude that that the vaccinated group must affect the chances of paralytic polio, because having only 33 wouldn't be consistent with what we see if the null hypothesis would be true. Okay. Um, there's another way to do this. We can use the built-in commands in R. We need to tell it what the contingency table is. So here's the contingency table. And we can do the Fisher's exact test. This is a less because in our null hypothesis, we said that it reduces the amount of paralytic polio. So if it reduces it, that's called a one-sided test. It's less than or equal to. And we return the p-value and we get 4 times 10 to the minus 12th. And so we get the same answer. There's some minute differences. But these two things calculate the same probability, and they can be used to assess the null and the alternative hypothesis as well as the data from a 2 by 2 table.